Greetings. I'm going to continue with the theme of work and energy, and in this case I'm going to think about, let's say, a block that is sliding along this way and experiencing a force due to friction. So it's moving this way. This is its velocity, initial velocity, and it's experiencing a force due to friction, which I'll draw in red here. It's a kinetic friction, and let's say that that's the only horizontal force it's experiencing. Of course, in the vertical direction, it's experiencing the force due to gravity acting down and the normal force acting upward. So in the y direction, I could say Fn minus Fg equals mass times acceleration in the y direction, which is 0, because the object's not flying up off the ground, nor is it sinking into the ground. So I could say, based on that, that Fn equals Fg, which is nothing new. It's the kind of thing we've seen before. In the x direction, I can simply say that the only force I have, so in case you've forgotten, this is all Newton's law that I'm writing down. It's F net equals ma in either the x or y direction. That's how I got this for the y direction. In the x direction, the net force is minus the force due to friction. That's equal to the mass of the object times the acceleration in the x direction. So the acceleration in the x direction then is negative because it's slowing down, which you'd expect. If there's friction acting on it and it's moving with some velocity in this direction, it's going to slow down until it stops. So the acceleration of the object is going to be equal to minus the force due to friction divided by m. Alright, so I could then go ahead and apply the kinematics equations and solve for this object's slowing down using the relation between Fk and Fn, saying that Fk equals mu k Fn. Therefore, acceleration in the x direction is equal to minus mu k Fn divided by the object's mass, and since Fn is equal to Fg, this would become equal to, I'll have to go to the next page. So I'll rewrite what I had earlier. I had Fk equals UK Fn, and I also had that acceleration is equal to minus mu k Fn over m. This is just to remind you what the last equations I wrote were. So Fn, don't forget, is equal to Fg. So just to remind you, Fn is Fg. So I could rewrite this as Ax equals minus mu k Fg over m. But Fg is mg, so it's equal to minus mu k mg over m. And cancel the m's, and I have minus mu sub k times g. It's the acceleration in the x direction. Okay, and then I could determine how long it takes the object to stop. So, or how far it goes. I'll determine how far the object moves until it stops. So I could say, okay, there's an initial velocity and there's this acceleration here. So the final velocity squared equals the initial velocity squared minus 2ax times x final minus x initial. And this is what I'm looking for here, this term right here. Alright, so my final velocity, of course, if my object stops, is 0. My initial velocity of my object is whatever it happens to be. I called it vi. And my acceleration is this guy right here. So put that in there. Alright, so I will move to the next page and I'll solve for this term here. So I have one correction. This should have been a positive here. It's going to become negative because of this, but it should have been a positive. Okay? X final minus x initial equals minus v initial squared, because v final squared is 0, and I move v initial squared to the other side, divided by 2 times the acceleration, and this is the x acceleration. Alright, so I just solve for the previous equation right here, and v initial squared is whatever it is, so it's equal to minus vi squared divided by 2, and my acceleration we came up with was minus mu k times g. Alright, so x final is going to be equal to, and I'll just take my x initial to be 0. So x final becomes equal to vi squared divided by 2 u sub k g. Okay, now I'm going to do the same problem, but I'm going to do it, instead of using kinematics, I'm going to use something called conservation of energy, or actually the work energy theorem, which is going to be saying that the friction is putting work into the object. So I can figure out how much work the friction is putting into the object and come up with the same expression, perhaps in a slightly simpler way that will be useful in other situations. And here that is, that equation right here. Okay, that's it for now. Now I'm going to solve the same problem of the box coming to a stop here. Like this. Say it's moving with some initial velocity v, as we talked about, and that it has this force of friction acting in the opposite direction, and that it's acting over this distance. I'll call it x final. I'll say my x initial equals 0. This is my x final. Okay, so what I'm going to say now is I'm going to say, well, the work that's done by the friction is equal to the force of the friction, which is in the negative direction, times the distance over which that force acts, which is this distance here, 0 to x final. Okay, so this is the work done by friction. Alright, so that work done by friction is equal to the change in the energy of the object. So that's basically what the work kinetic energy theorem tells us, is that the work done by something causes a change, results in a change in energy of the object that's equal to the amount of work done. Okay? And we talked about in class that the energy of an object, if the object's moving, that energy, there's two kinds of energy, potential energy and kinetic energy. That if the object's moving, it has a kinetic energy equal to 1/2 mv squared. Okay, so if that's the case, and this object has a mass m, then that means that this object has a kinetic energy of 1/2 m times v initial squared. And what we're also saying is that that energy here is the energy that's lost. So the object's going to lose all that energy. It has all that energy here. When it comes to a rest at this point here, it will have none of that energy, and all of that energy would have been converted by friction to heat, basically. So the friction's thing doing the work to stop that object, and it's causing that energy to change, or it's doing that amount of work on that object to slow it down, and that becomes heat. Alright, so what I'm going to do then is I'm going to use that to try to solve for this final x position of the object. So I'm going to put on another slide. So what I have here then is that the work done is equal to the change in object's energy. And if I calculate that out, I'll say the work done is equal to the force of friction, sorry, it's Fk, times x final, that's negative. It's equal to the change in the object's energy. Well, the change in object's energy is the object's final energy. I'll say its final kinetic energy, well, I'll use Ke as the symbol for kinetic energy, minus its initial kinetic energy. Alright? Its initial kinetic energy was 1/2 mv initial squared. Its final kinetic energy is 0. This force due to friction is equal to mu k times the normal force of the object, and multiply that times the final position of the object, and put a negative sign in front of it. That's equal to minus 1/2 m times v initial squared. And then the only thing I need to do here is know that the normal force is equal to the force due to gravity for this object, which is equal to mg. So if I solve for this whole expression, I have minus mu k mg x final equals minus 1/2 m v initial squared. Cancel out the m's and solve for mu k, and I will get mu k equals 1/2 v initial squared divided by I'm sorry, not solving for mu k, I'm solving for final x position. X final equals 1/2 v initial squared divided by g times mu k, which is the same equation that I had earlier. I'll pop that up just for a moment to prove it, but this here I used energy principles to come up with is the same equation that I came up with a moment ago.